From the time when I was a student, I remember very well that the lecture immediately after the lunch break is the most unwanted one, because everyone is still sleepy. I want not to continue to contribute too much to the sleepiness, I hope, and I would like to do it as I did it in my first lecture this morning. I will split it into 2 parts and have a 5 or 10 minutes break in between to get a little bit more clean-minded again. Problems of SLR system calibration is called, and what I want is to raise a little bit of understanding why I'm stressing that so much, because I think our session is called Challenging Problems of Satellite Laser Ranging Technology, and one of that challenging problems is the improvement of the accuracy. I've spoken on Friday about upgrading the space segment. I've spoken which efforts were made in the ground segment to reach that by principle, but the best effort you can do, both in the space segment and in the ground segment, will fail in case your system is improperly calibrated. Just an example from home. In case you want to measure the length of this desk by a simple ruler, and your ruler is short for 2 millimeters, you will have a systematic error, an error in the scale factor. This is the first problem you can have. And in case you do not start measuring the length or the width of this desk at the edge, but start about 3 or 4 centimeters from the edge using a perfect ruler, you do not have a problem with the scale factor, but you have a bias, you have an offset. These are the 2 basic errors you can make in any measurement system, and the satellite laser ranging makes no exception of this. A short overview of the topics, only very few sentences about the principle again. I stressed it in the morning and on Friday again. The system delay in satellite laser ranging was addressed also in Jorge Del Pino's presentation on Friday. I will come back to that, just to refresh the memory. And then we go to the principle of SLR system calibration. We look for a calibration scheme in case you have a monostatic system. Monostatic means that transmitter and receiver are not separated. You have a single telescope which is performing both the emanation of the light and the reception of the single photons. I show you examples for real calibration runs, how they are performed, how they are processed. It looks very simple, but you have to take care of the thing. We do it first for a short range and then over a longer range, because both methods are feasible. The system calibration scheme for a bistatic system, that means when the transmit telescope and the receive telescope are separated, looks a bit different, but I will show you an example. Then we come to a very important point. Is there a possibility to make an external verification of the system calibration? The idea behind is the following. You do your best effort, you are fully sure. I have a ruler, which is according to all the standards. I start at the very edge of the table. I will have no bias inside. But is there a method to verify if I'm really doing my job well? Is there an external verification which does not depend on me, on personal skills, which is independent of the station itself, which is done by external institutions? We'll give some examples of target calibration statistics. Jorge Del Pino got the brilliant idea several years ago to record not only the mean value, the standard deviation as is required, but also the higher moments like bias, skewness, kurtosis, and so, which tells you a lot about the behavior of the system. And finally, I will turn to a thing which may be a little bit outside, but for the calibration you need in any way the invariant point of your system. And how do you get it by a survey? And how do you perform a geodetic survey in a larger area? And finally, I will draw some conclusions about what we've heard. You will see where we make the break in between. Let's go not too fast. Again, the principle of satellite, laser ranging, transmitting a short pulse toward the reflector, receiving part of the light back, measuring the two-way traveling time, multiplying by half the speed of light for the vacuum part. Take into account the atmospheric delay for the path of the ray, of the pulse, which is traveling inside the atmosphere. This would be a lecture as well, because today you have several atmospheric models for correction of laser ranges which have to be applied, but this atmospheric delay has not to be applied by the station itself. The station itself can give some proposal for data reduction, for filtering, but afterwards the approved method or the used method is reversed. The atmospheric delay is not considered. This has to be done by a computing center, by the data processing center.
Do this atmospheric delay depend on the day, particular day,
Yes.
and the type of
Yes.
weather?
Yes.
And
It depends on several factors. It depends on the ground parameters of the atmosphere, like pressure, temperature and humidity, mainly on pressure and temperature. Humidity has less influence. It strongly depends on the wavelengths you are using. And this atmospheric delay is only an integral value you get. Because you are going through the atmosphere, you do not see if there are any gradients in between. So the accuracy is limited from the very beginning. If there is strong turbulence, for instance, these days in the higher atmosphere, you will get some scattered noise you are unaware to see because you record the static values of temperature, pressure and humidity.
And is there any other parameter of a laser which is used for this purpose other than wavelength, like intensity,
No.
flux?
No.
No?
This is not, fortunately this is not foreseen because we are working anyhow in the low signal level method. So in case you would have a high power laser, let's say kilowatt or a terawatt or something like that, a continuous wave, you are right, then there would have to be some self-focusing and something which could give rise to secondary effects. Fortunately, we are far away from this energy density, so we do not have to take it into account. And today, this atmospheric delay can be applied both as a closed arithmetic formula or as a grid function, that you subdivide the sky above you into grids and do some sophisticated modeling. I think it is still a question of taste, and I think the atmospheric delay application is today the ultimate limiting factor of accuracy for the satellite laser engine. Because we have problems to measure it. The very moment the laser is working, there were some attempts in former years to do it on two wavelengths separately. Because in case you do it in two separated wavelengths, you could work in a differential way. It's the same as you do with a dual frequency GPS to take out the ionospheric contribution. But these days appear over to me. I've not heard for a long time about successful two-color ranging. So the atmospheric delay is determined today in a way that you combine both measurements down from the satellite towards ground and compare it, for instance, with radio sound data from the ground going up to the stratosphere.
So this is cross-checked with the experimental value and with the
this is cross-checked with experimental value for different parameters on ground. What we are talking about today is the system delay, because we are measuring always a priori time of flight or distance of the satellite, which is too long.
Lutz,
Yeah.
maybe I can make a comment, you will do it also. There are two problems also, that the meteorological station should be fully calibrated, so the pressure and temperature we are reporting to the centers is the real one, and the second thing that the position of the meteorological service of the local from the observatory should be very well referenced to the position of the telescope, especially for pressure. The difference of heights should be known to a millimeter minimum to make some local compensation.
Okay, the question which was answered by Jorge already on Friday, I will take it again. Why is there a system delay in satellite laser ranging? Let's look into the block scheme we have here. We have the laser pulse generator, which is fed into the telescope and transmitted towards the satellite. We have a small correction on board of the satellite. I spoke about that in the morning. The center of mass correction for the laser ranging reflector array. The transmit telescope brings the light back towards a detector. And also the laser pulse generator needs a detector because we are performing our measurement using light pulses, but the light signal cannot be directly used as a trigger for the ranging electronics. It has to be converted into electrical signal by photodetectors first, and then the detector is not sitting on a zero distance from the time interval counter. All the electrical signals from detectors, both from the start and from the stop, have to be routed via cables to the ranging electronics. That means all these processes require some time, and consequently the raw measurements are too long. It means this excess time, which is contained in all the measurements you have, has to be removed from the data. And this is unavoidable. It is not because you are not doing your job very well, it is unavoidable. The system delay has to be found by a method we call the system calibration. And that's what we are talking about. The principle of the SLR system calibration is extremely simple. The principle. As usual, principles are always simple. The problem is how to perform it. You have a telescope with an invariant point. I'm coming back to that in the later part of my lecture. And you have a flat target. I'm stressing the word flat, and I will tell you again why. At a known distance d. You fire laser pulses towards this flat target d, distance d, and record the time it takes to perform this measurement. The time of flight you are measuring is twice the distance divided by the speed of light. Now I take only the c in general. In principle I should take the reduced speed of light in atmosphere, but I will come to that later, plus what I sum among the word cable delay. Cable delay is all the electronic delay which in this SLR system cables, converters, detectors. It is very important to attenuate the signal in a way that the average return matches the return rate during real satellite passes. For those who are not performing satellite laser rangings every day or every night, the return rate from an average satellite is in the order of few percent best. It means only every hundredth or every 50th or so from the pulse gives a return. And I'm reading, or I'm stressing this, avoid signal-dependent time warp. I will tell you why. I have here a real calibration of mean value for a target run via the signal strength of photons. We have attenuated our signal towards the flat target in different ways. We have removed neutral density filters in order to get a signal composed of more and more signal photons. You can get the number of photons by some Poisson statistics. I will not stress that here. This is a straightforward way. All what you have to about one average photon is in the order of a return rate, which depends a little bit on the quantum efficiency of your receiver, of less than 20%. So up to here, we have return rates which are, let's say, 5%, 4.1%, 10%, 15%, but not more. For higher return rates, let's say 50%, 30%, then we immediately see the slope. And for 10 and more, 20, 30 photons average signal, the curve has a very steep slope. That means if the signal strength for calibration does not match your level, in case you apply a too high return energy to the calibration, you get here a shift with respect to the average you should have in the low signal level, where you are performing your satellite measurements. And it sometimes to be observed that the operator of the system says, now calibration, I'm hungry, I'm sleepy, I want to go home, let's take 50% of return rates, then it's over in 1 minute. Nice, but you get an unavoidable shift in this case. Here we are on the order of 100 picoseconds. 100 picoseconds sounds not much, but it's in the order of 1.5 centimeter. And in case we are talking about millimeter, that's bad.
Can you please go to the last slide? So here, as far as I understand, there is a contribution of this atmospheric delay for the electron.
You will see it. I will give you some numerical examples.
Yeah, because the D, which is in this expression, will be different if the weather conditions are different, depending upon the velocity.
The D is independent on weather conditions.
No, but if you
the time of flight, the C
yes,
is a little bit.
I mean time of flight,
yes,
right?
Yes.
Because the C will be different for the different atmospheric.
Right. But you will see, in case we do not exaggerate the distance of the target, you will see it is manageable. I have some numerical examples for you later. So, and when we know the theoretical time of flight over the slide, short distance, short or a little bit longer distance d, then we can subtract the theoretical time of flight from the measured time of flight, and
to find out the error here,
we have the cable delay, which is the subsumming of all the elements, the cables, the converters, and the detectors. And the cable delay should be independent on the range and distance. This is very important, because it is not possible, or it would be a very bad misconception in case you derive a cable delay, let's say over 10 meters, which is different from measurements to satellites at 10,000 kilometers.
Yeah.
So this is the basic idea behind the calibration. The delay you find out, the system delay, has to be independent on the distance you are measuring. So we look for some scheme. How can we perform it? We have here a TPL telescope. The main tube is dismantled. You see the main mirror. You see this 1 meter mirror. Mars is here standing in front of that, attaching an alignment device. So you see it's a huge machine. And where can we apply a target? Where can we apply a flat target? In a shot taken from far, here is some holder, and here's a very small single tube corner. A single tube corner is as well suited as a flat target because it does not introduce any target signature. In the morning I've shown you that an extended target, like a large satellite, gives rise to a signal deformation on the way back. In case you have a flat target or a single tube corner, the signal is ideally sharp, because you have only a single point of reflection. This is very important. So we use either a flat target or a single tube corner in front of the telescope. This is the general scheme of such a monostatic TPL telescope. The main mirror, the secondary mirror, the laser is going via those mirrors, via a rotating mirror, which is in place just when the laser is fired, into the hoodie mirror, and is transmitted toward the satellite. And the returning signal goes this way, and in case the signal returns from the satellite, is reflected on the main mirror, on the secondary mirror. The transmitter is not in place. It goes this way to the receiving mirror, which is then in place, and goes into the detector. This is the full light path. This cannot be achieved in the usual convenient way, so we couple a small part of the light via a sideway to a wall target within short distance, receive a small portion of the light via a prism, and feed it directly into the detector. This is the way as it was proposed by the designers of this TPL mount, and this is the principle okay, but it has a problem. This part does not include all optics, and it has to be calibrated as well. Because when we are starting to couple out the light from here, we are missing the path through the main telescope, through the secondary, through the main mirror, and we have to know how this delay to the side path, which we are measuring here, is to be related to a distant target. And that's why we modify now the scheme. The image I have shown you before shows a very small target, there a small cube corner in front of the main telescope. Again, we have the laser, no idea, or no, not interesting how it is called. This is a self-made one in Potsdam. The light goes via just two mirrors to the rotating mirror, goes through the complete telescope, and is reflected back from the cube corner in front of the main telescope. It's going immediately back this way. Now we have a problem. The transmirror, mid-mirror, is still in place. So, in case we do not do anything, the light would run back into the laser and we would have no stop signal. So we have to make the transmit mirror slightly transparent so that this very, very small portion of the light can go through this transmit mirror, which is still in place, to the fixed receive mirror. We do not let it rotate at this moment, and the light is going back into the detector. So the complete electronic, this is the complete optic signal path. The electronic signal path is a little bit different. The pulse from the laser is going through some attenuating neutral density filters into a photodiode. This photodiode signal is fed through a Tenelec, through a constant fraction discriminator, into the start of a time interval counter. As an example here, the famous Stanford Research 620. And light from the receive part is fed into a photodetector, let's assume a photomultiplier, with a preamplifier, is going through a Tenelec, again with the second channel of the Tenelec, into the stop of this SR620. In between are several cables. So, and now our task is to compare this optical light path to the cube corner and back with the complete electronic signal path through all these cables, converters, detectors, discriminators, start and stop triggers. This is the main idea. So let's look how this is looking for. Let's now place our small single tube corner in front of the large TPL telescope, and we are recording a sufficiently high number of laser returns from this target to get a statistically significant reading and a reasonable standard deviation. In case the observer operator of the laser system remarks that the statistic looks bad, that in a case that there is a too large scatter, or somehow the signal looks not very nice, he should do his best to avoid such effects. We compute the theoretical time of flight of the light over the target distance. This is 2d by the speed of light in vacuum. And now we correct the theoretical time of flight in vacuum for dry air according to theoretical time of flight multiplied by the index of refraction of dry air. And this is what your question is addressing, because this index of refraction of dry air is not the same every day, at every temperature. Now we find the system delay in very simple run as the difference of both methods. T system, which is the system delay, is the measured time of flight, the significant mean value, minus the corrected theoretical time of flight. And let's look how this is giving values for a very short target distance. This is a real calibration we have performed in Potsdam with this TPL system. The mean is 50.876 nanoseconds. The small prism is attached at a difference of 1.144 meter with respect to the invariant point. We'll get back to the determination of the invariant point later. That gives rise to a theoretical two-way traveling time of 7.632 nanoseconds. If we correct it, going into the table for dry air at 20 degrees Celsius, 1.00026, you see this is not deviating too much from 1. We enhance this by 2 picoseconds. 2 picoseconds is practically nothing. This is less than a millimeter of flight time. And we get the system delay as 43.233 nanoseconds. We keep that in mind, but we will see it on a later slide again. This was a short way. Now let's look to the right picture first. You see again the small prism here in front, but now we look to this strange figure here in the background. In the opposite way, it means upside down, you see in the main mirror the image of the nearby Helmut Tower. This is a very famous geodetic building in Potsdam, which was carrying the first laser ranging system. First and second generation we were operating from 1974 to 1993. The so-called Satellitenbeobachtungsgerät, or SPG, a formerly pure photographic tracking camera for satellites. There was also one in Riga from the same type, which was later modified for satellite laser ranging and transported to Santiago de Cuba. We will see it again, formerly Riga instrument. So, and during a survey, we placed over one of the markers, which were there on this well-known Helmer Tower, the prism, after we had measured by tachymetric measured the distance to the invariant point and performed directly ranging from this telescope to this prism, which was standing at a certain distance on top of the Helmer Tower. So over longer range, the system calibration from the principle is the same, but has to take into account a little more. First is the same, you record a statistically significant mean and standard deviation, and then you have to find out the target distance. You need three-dimensional topocentric coordinates. The invariant point has the index t, and the cube corner reflector, which is point over one of those markers, has the index c. You find out the distance d by this simple equation. We compute the theoretical time of flight. Here again, the speed of light in vacuum, corrected for the dry air. We find the system delay in the old-fashioned way. Now, let's give you an example. Because our tachymeter was placed just above the CCR, we have two of the three components, of the three rectangular components of the coordinates equal 0, and have only to find out the height on the tripod. The invariant point was measured from there to be minus 25 to the north, minus 26 to the east, and minus 13 in elevation because the tower is higher and the satellite station was on ground. The time of flight now considerably larger. The theoretical distance computed according to this formula, 40.2 meters. The theoretical two-way time of flight, 282.06. And now you see the correction of the dry air is considerable. It's about 70 picoseconds. This is in the centimeter area now already. And you get a system delay of 43.229. Let's compare the two ways. We have a short way over a distance of 1.14 meter. We have a long way or a medium way. This is a question of taste, 40 meters. Theoretical time of flight in vacuum, corrected for dry air, and you find a system delay which coincides to about 4 picoseconds. 4 picoseconds is for a laser ranging system of the third generation as it was used for those calibration runs, a very good coincidence. That means the obtained system delay is independent on the use distance. It has to be independent, otherwise we are lost. In case we cannot determine a satellite laser ranging system delay independent on the target distance, something is wrong. But we prefer a shorter way for the target calibration because the influence of the dry air grows with growing target distance. You see, we corrected against the theoretical value in vacuum 70 picoseconds, 2 picoseconds for the short way. And also very important, you can locate the short way target within the station building, and thus the calibration can be performed even when there is no visibility to the external target. We started in Potsdam when we were using the first and the second generation laser ranging system with an external target at a distance of roughly 2 kilometer distance. It was located at a fire watching tower somewhere over a forest area. It was quite nice. We could use it both for aligning the parallelity of our optical axis, and we could use it as a reflective target. But especially in autumn and early spring times, it was nicely visible in the evening, but in the morning the fog started to raise. The sky above you was still clear. You could track satellites, but you could no longer see the target. You could not perform any target runs anymore. so you could stop satellite laser ranging because you had no reference point. And that's why we try to find as soon as possible possibility for a short-wave target. And I will give you an example of such short-wave calibration target. This is the formerly Riga, now Santiago de Cuba target. We have here a laser which has to be set up and moved together with a telescope. There is no other possibility, there is no choice to have a coude pass. This is a question of the optical design. This telescope was by construction never foreseen to be used as a laser ranging device. And now we have a very clever device in front. This is just a bar of metal. Here is a small hole, and the white paper, the laser pulse, is getting through this hole and is scattering into the 2 pi area angle, and a very small part of the scattered light is getting down on a second scatterer, which is not illuminated because it's night here, on a white paper again, is collected there and is fed through a thick neutral density filter into the main tube of the telescope where the detector is. So we attenuate 2 times, practically everything already here. You see practically no laser light with your bare eye on the second scatterer, and what is going into the tube is even less. This is the method of obtaining the same signal level as during satellite laser ranging. There's also another method. We see here the very famous and excellent laser ranging station in Graz, in Austria. They do not have the possibility to attach a metal bar, but they have another trick. This is the small telescope which is attached to the 60 centimeter aperture main telescope where the laser is fed through. And the receiver is this large telescope. It's a 2-axis mount. In principle, is a monostatic, is a half bistatic because the laser is getting through this part, to the side of the telescope, is going into the separate telescope, but the distance is so small that we can still consider it as a monostatic. The laser is fired through this hole. Maybe you can barely see it here in this black hole, in this black box. The laser is firing. You see here a green light. So there is a scatterer. The second scatterer is there on the other side, behind some neutral density filters, and is scattered back into the main telescope. Twice scattered, twice 2 pi angular angle, so we get the proper attenuation. In the case of a real bistatic system, these things look a little bit different. We have here an example of the 4th generation, or 3rd and 4th generation system, where we have 2 separate telescopes. One telescope is entirely intended to transmit a laser light, and the other telescope is intended only to collect the laser light coming back from the satellite. Those telescopes have to be controlled fully in parallel. But both telescopes are mounted on the same steel base and on the concrete pillar on this tower, but they are separated by about 2 meters. And this is a problem. You cannot use an external target. It's not feasible. In case you would like to use an external target, you would take into account that the field of view of the receiver telescope overlaps with the beam from the transmitter only at a distance of several kilometers. I have made a computation in mind, and it should be about 8 to 10 kilometers before the receiver telescope sees the beam from the transmitter. Only at a distance of 2 meters. This is because of the narrow fields of view. So you are lost with an external target, and you can only use an internal or short-wave target. And fortunately, there's a very simple way to perform target calibration for a bistatic system. Georg Kirchner from the Austrian station had a clever idea. He said, "Hey guys, there's a very simple way. Bring just both telescopes in the opposite position. Bring the transmitter directly anti-parallel to the receiver. This is the receiver. You see the output of the transmitting telescope. Here's the transmitter. Here you see the input of the received telescope. attenuate the transmitted light pulse from the laser to a level as during satellite observation. You can use a strong neutral density filter. Of course, you have to take into account that this neutral density filter is not inside your path during satellite laser ranging, but it can be corrected easily, and fire directly into the receive telescope. Then we have again the theoretical time of flight for the laser pulse in the case of a bistatic telescope, but this T theoretically is this time not 2 times d over c, but only d over c, because the invariant point is just mid between those telescopes. This is the difference. So the basic principle is the same. Let the light run over a dedicated, very well-known distance and record that. And now the big question: can we prove that our system delay is correct? Yes, it can. I would say fortunately, some stations may say unfortunately yes. There are 2 geodynamic satellites in orbit since 1976, MAGES and its twin. MAGES 2 is a joint US-Italian project launched in 1992 together with its upper stage from the space shuttle. They allow for an ultra-precise orbital analysis. And we have 5 independent data centers around the world who compute the MAGES orbits from SLR data only. And they are so precise because those satellites are so heavy, about 400 kilograms each. They are orbiting at an altitude where practically only gravitational effects and play a role, and the other effects are very well model level, for instance the radiation pressure from the sun, unisolar tides and other things, so that the orbit, the mean orbit of those 2 satellites can be averaged over 1 week in the order of 1 centimeter. This is an orbital diameter of 25,000 kilometers. There is 6,000 kilometers of satellite orbiting altitude, 13,000 kilometers of Earth diameter, again 6,000 kilometers of satellite altitude, and this huge orbit can be modeled very precisely. And those individual measurements from the single satellite laser ranging system are compared against the adjusted orbit. That means you do not know it immediately. You need a few days until the precise orbit is adjusted, and you solve for range and time bias for every station. Of course, the accuracy is only within the achievement threshold of the MAGES orbit. It means everything what is in the order of 1 centimeter and below is just at the limit, but above is clear. Here's an example, very recent, from the beginning of October, just before I packed my luggage. I got this email from the University of Sinnerwald, where they collect all this. We have here the first center of the Deutsches Geodätisches Forschungsinstitut, the German Geodetic Research Institute in Munich. We have the Mission Control Center in Moscow. This line is empty because the colleagues in Moscow are a little bit late. They deliver their analysis 1 or 2 days late, so that it's never contained in the very recent analysis, but it is contained in the quarterly analysis, which is performed by the IRS. We have the Hitotsubashi University in Japan. We have the Smithsonian Observatory in the United States. The same problems as with the Russian colleagues. They deliver their orbits late. And the JCIT, also in the United States. Ecuador. You see, LAGES 1, LAGES 2, mostly LAGES 1 for the moment, the wavelengths, and you get a range bias per pass and a precision per pass. That means the precision is more or less the scatter in millimeters. All this is given in millimeters. And you see, you will practically never see the same, exactly the same result, with a rare exception, for all those centers, because they have their own modeling philosophy. But the averaged value over 1 week or a little bit more is giving you a value if your system is well calibrated or not. Of course, you have some runaway point. GCIT obviously had a very bad day, assigning us a 5 centimeter range bias, while Hitotsubashi said, no, you are 1.5 centimeters short, and GGFI said, no, they are 7 millimeters long. So they cannot coincide to the ultimate level, but in general, in case there would be a trend, you would see it here in the averages. So that means, fortunately, in case I get such an analysis, I said, okay, We have performed the proper analysis, the proper range bias by applying the proper system delay. We have delivered the proper meteor data because what Jorge Del Pino just mentioned fully correctly, in case I deliver wrong values for pressure and temperature, I will be assigned a range bias as well. Let's look shortly on some calibration runs before we make a short break. As I told you, Jorge Del Pino had the good idea to record not only the mean value and the deviation, but also higher moments. This is a screenshot of a calibration run from our third generation system when we are still using 10 Hz repetition rate. In the middle of the screen there is the expected time of flight for a calibration run, and the computer selects by 2.5 sigma criteria the points he likes. He is assuming those to be real target returns, and computes from that real-time histogram. You see immediately it looks not so bad. There are some side peaks, but they do not matter too much. After you have finished with your runs, we have performed here about 1,000 shots. Here 949, you get the mean value. The scatter is about here in the order of 68 picoseconds. You get the standard deviations, skewness, kurtosis, bias, and so on and so on. This is a run in 2009. It is stored as an Excel readable table. This is a good thing because you can use it also decades later. Excel is on the market already for a long time, and there is no sign that it will disappear. And here is an example of a calibration run recently when we had switched over from 10 Hz to 2 kHz and using a single photon avalanche detector. This is what we call SPAD as a detector. Now you see the line in the center is much more populated because we are performing usually about 10K of returns. It takes only very few minutes. The average return rate is in the order of 5%. It's not very well readable, sorry for that. The mean is about 78.5 nanoseconds, and the standard deviation per shot is in the order of 15 picoseconds only, because we have a very short pulse laser and a high-speed photodetector. What you get from your calibration, and that's why I stress those two different calibration runs, is the system response function. In case you average over a large number of target returns, because the target is flat, then you see what your ranging electronics in combination with your detector, your time interval counter, your laser pulse width is giving. This here is a quite symmetric distribution. This small secondary peak is a reflection within the system, which does not contribute to the system. During the 2.5 sigma filtering, it will be cancelled out. This is a PMT, and this is a SPAT. You see the SPAT is much more narrow. It's very nice, but it has a very long tail. And those of you who may have some studies in semiconductor physics immediately know that there is some trapping process within semiconductor material. That means some of the carriers are captured for some time in the semiconductor material in what we call shallow traps, and are released a few hundred picoseconds or nanoseconds later. It means we have to cut out this tail. We have the Hamamatsu 5320 or the MPD1CTC, and you get immediately the system response function, which is given for the hardware function and is mainly governed by the parameters of your system. And this response function is not needed for the SLR immediately, but in case you perform some high-level studies, as I have shown in the morning, to find out the center of mass correction for spherical satellites, this is looking different. And 2 or 3 more slides before the break. Few statistics of the Potsdam system calibration end of 2013 up to now. You see the return rate is always kept, shall be kept below 10% or not much more, but sometimes whether the automatic is failed or the observer is lazy and says, oh, I want to go home, why not perform the target run with 65% of return rate? Of course I have to eliminate it. In case I accept this calibration run, I will be assigned a range bias. The acceptance rate is more or less constant, a little bit before 90%. Here was a gap. the laser was broken. We had to wait for the enterprise to repair. We came back into business early September. From that, we have stable return rates. And I told you that Hora is not only recording the mean and the scattered value, but also the bias, the kurtosis, the skewness. This kurtosis of 2.6 says that we have a more or less symmetric pulse. There's not too much leading and trailing edge difference. And also skewness, it is not too much inclined. The skewness you can imagine as the inclination of this distribution. You see over 1 year, the scatter is relatively slow. Please look to the scale. There's practically no deviation from the average. And as the last one, there's always the question, oh, in case this is so constant, your calibration, why do you perform it? We simply write in the same value every night and every day, and we are fine with that. Why are you wasting time? It is not. For the same time, let's say starting end of December 2013, till about March to April, everything was fine. We had an average value of 90.39 nanosecond with few scattering, but then we saw a decline. The system was degrading. In April, we suffered the failure of some of the laser stages, so we could not pump the final amplifier anymore. We had to switch to a low energy modus, and even the oscillator degraded more and more. The pulse amplitude went down, and you see immediately here the slope. When we came back to business after the laser was repaired, we had both a new average value because the system was realigned, and now it is looking much more stable. So, in case we would have applied this value for March, in April or in July, we would have been assigned a range error, a ranging bias, in order of a centimeter, which is a shame for a fourth generation system. And now we are back to that. So the range bias cannot be assumed to be constant. The system delay is never constant. You have to measure it because the system delay contains all the relevant parameters of the system. This is my most important measure. Do it as often as you can. Don't say, it will be the same tomorrow, mañana is also a day, and let's assume that it to be constant. It is not. And sometimes I see presentation, we have introduced a new system, and now our system delay is flat to in a tenth of a millimeter. I do not believe that. Okay, let's have a few minutes back.